Okay, guys, we're going to start topic 8.2 on thermal energy transfer. So, our learning objectives are to describe the greenhouse effect. So, by the end of this lesson, you should be able to do that. You should also be able to explain albedo and calculate energy transfer using that. You should also be able to apply the Stefan-Boltzmann law to solve energy balance problems for the planet. Okay, so here's a little humorous cartoon to get us started. I'm sure you'll find it hilarious. Hilarious. Okay, moving on. First thing we need to talk about is the solar constant. So the sun has a total power output of 3.9 times 10 to the 26 watts, which, as you can see, is quite a big number. This value is also in your data booklet. Convenient. Only a little bit of this power, relatively, reaches planet Earth. And the amount that arrives on planet Earth is given by intensity, which is power divided by area. This value is indeed in your data booklet. So the area is the surface area of a sphere of radius d, and that radius is the distance from the sun. In other words, Earth's distance from the sun. Okay, so we then use the surface area of a sphere and we plug it into our equation and we get intensity equal to power divided by the surface area of a sphere. And this value is, just FYI, not in the data booklet. Okay. We then find the radius of planet Earth, and we note that it is 1.5 times 10 to the 11 meters. And we can plug that value into our equation. And what we will find then is that the intensity of light instant on planet Earth is 1.36 times 10 to the 3 watts per meter squared. This value is our solar constant, and that is in your data booklet. Also, I need to work on this slides animation a little bit. Okay, so the solar constant then is given by 1,360 watts per meter squared. Your book rounds this off to 1,400 watts per meter squared. That's fine. Note that what we're actually looking at here is an average value because the power output of the sun can change a little bit, plus minus apparently about 1.5%. The distance from the sun also changes, and the angle of the Earth's surface will change as well. Okay, so we have a few things going on here, and what we're talking about then is an average over time. Okay, so this power per meter squared can only shine on a cross-sectional area of the Earth, okay? And the formula for circular area, so what we have here then is effectively a circle, and the area of the circle is, of course, pi r squared. In this case, the radius is the radius of planet Earth. Okay, so here we see Mr. Sun shining directly on the planet, and this slide just shows the effective arrival of the solar radiation on the surface of the Earth. And the amount of radiation arriving is given by the amount shining on the disk. So if you cut the Earth in half and calculate the amount shining on that cross-sectional area, you would get a diagram that looks something like this. Okay, so Interestingly, our solar radiation is distributed over the area of a sphere, not the cross-sectional area. Okay, so that changes then a little bit how we approach this. So conveniently though, the area of the disk is given by pi r squared, and the area of our sphere, the actual surface area of the planet, is given by 4 pi r squared. And you'll see why this is convenient in a second. It is convenient because what we have then is a ratio of 1 to 4 between the area of the disk that the sunlight is effectively shining on, and then the area of the sphere where that intensity is effectively distributed. Okay, so what we do then is we average out the intensity of sunlight reaching any area on the planet, and what we find is that the actual average intensity is equal to our solar constant divided by 4, and that gives us 340 watts per meter squared. So if you were standing at any point on the planet, the average intensity of sunlight is going to be 340 watts per meter squared over time. But obviously it's going to depend on where you're standing, what time of year it is, etc., etc. Okay, so this value is going to fluctuate. So this GIF shows the predicted increase in temperature. A lot of it is going to occur at the polar ice caps, which is problematic because due to convection currents, those polar ice caps are actually driving a lot of the climate systems on the planet. So if they warm up, that's going to change the weather tremendously annually. Okay, so let's talk about albedo for a second. About 30% of the light from the sun is going to be reflected by the Earth and the atmosphere. Okay, so 30% of this light is just never going to arrive on the planet. It's going to bounce right off. Okay, so this gives then the Earth's albedo factor, which is about 0.3. Albedo is the ratio of reflected light to incident light, and we have a formula for it. Here it is. Albedo is equal to total scattered power divided by total incident power. And the little diagram there, I thought about taking it out, but I've left it in. It just shows that different surfaces have different albedo factors. So a high albedo means that there is more reflection and less absorption of energy. And a low albedo means that there is less reflection and more absorption of energy. Okay, obviously albedo can never be either 0 or 1. Maybe that's not obvious. So let me just say it. Albedo can never be 0 or 1. There you go. Okay, we previously calculated that the average intensity of sunlight incident on the Earth is 340 watts per meter squared, but we had not considered albedo in that previous calculation. So if 30% of the light is reflected away from the planet, leaving 70% absorption, then if we include albedo in our calculation, we will find that our average intensity now is equal to about 240 watts per meter squared at any given point on the planet. And again, this is an average, so that value is going to vary quite a lot. But there you go. So your SOCOS textbook gives a summary of the average intensity on a sphere as average intensity is equal to 1 minus albedo, the quantity 1 minus albedo, times S divided by 4, and we need to identify that S. It is the intensity of sunlight incident on the planetary disk. Remember, we have defined the incoming intensity of light as the intensity shining on a disk with a surface area given by the radius of planet Earth. Okay, so albedo is going to depend on ground covering. So ice has a high albedo and ocean has a low albedo, which means that water absorbs a lot of energy and ice does not. If we link this to global warming, you can see how this might be a problem. Cloud cover is also a factor, etc., etc., etc. So here we have 3 examples. Open ocean with a very low albedo, which means there's lots of absorption. Bare ice with a higher albedo, 0.5, which gives us some absorption and some reflection. And ice with snow, which is our best possible albedo, 0.9, where the Earth would only be absorbing 0.1. Anyone who's been skiing will recognize that this is true because you need to wear goggles or you will go blind. Snow blindness is actually a thing where you just can't see. You cannot see, it's too bright. Okay, so this diagram shows the power delivered to the surface of the Earth. You can see the incoming intensity I there, and this would be the sunlight coming in. Okay, we then have the reflected light, and this is simply equal to albedo times that intensity. So in the case of the Earth, that is 0.3 times the incoming intensity, and that will be the intensity of reflected light. We then have the intensity of light received by the Earth, and that is given by the quantity 1 minus albedo times intensity. And here we are treating planet Earth as a black body, so the intensity of the light radiated back into space is given by the quantity 1 minus albedo times intensity. That is the same as what is received by the Earth. So assumption, the Earth is a black body. Okay, this absorbed solar energy is going to be re-radiated at longer wavelengths. Okay, there is a simulation here that you could click on. I am going to share this presentation with you. So if you'd like to take a look at it, please do. So this infrared light is a little bit problematic because various gases in the atmosphere will absorb infrared radiation that they did not absorb previously. Okay, so they're going to vibrate more, and then they're going to release that radiation, as we'll see in a second. So these are what we call our greenhouse gases, and carbon dioxide, methane, water, and nitrous oxide are a couple of examples. Not the only examples, but the most common. Okay, so the problem here is that these gases are going to absorb the infrared radiation and then they will re-emit it. Okay, half of that re-emitted radiation will go into space, but the other half is going to come back down to the planet. This can get pretty complicated, as you can see by the Sankey diagram. You don't need to know it to this level of detail. What you do need to know is that there is a balance between the energy absorbed by the Earth and its atmosphere and the energy emitted. And historically, for the last several thousand years, many thousands of years, this has been pretty stable through the totality of human history. The last ice age was about 20,000 years ago, if I remember correctly. So what that means is we normally have a pretty constant average temperature, although, of course, there have been some big changes. In fact, we need the greenhouse effect because without it, the Earth simply would be too cold to live on. So the trapping of energy by these gases is not a bad thing under normal circumstances. However, the combustion, processing, and extraction of fossil fuels emit enormous quantities of greenhouse gases. And these gases then absorb the infrared radiation, re-radiate it back toward the planet, and the more of them we have, the more of this re-radiation we have. So it's not difficult to understand. This shifts then the equilibrium, and what we get is what we've been seeing over the last quite a long time, but it's accelerating now. What we get is a clear pattern of climate change. And this is called the enhanced greenhouse effect. Okay, so some consequences of that are the melting of the polar ice caps. As I said, this will affect global weather patterns tremendously due to convection patterns, and also because, remember, ice reflects a lot more energy than water does. So if all this ice melts, that decreases the albedo of planet Earth, and that is not a good thing. So if those ice caps melt, we also get higher sea levels, and that means that we get flooding in coastal cities, which, you might note, we actually live in. Okay, it also means we're going to have more extreme weather events, heat waves, droughts, hurricanes, torrential rain. I should add to this list fires, because California and Australia both have been basically burning down. Well, California has been burning down every year for the last 3 or 4 years. Australia now is also on fire, although I think they've largely got those under control at this point. Okay, sea level rise, mass migrations. There have been some studies that indicate, for example, the Syrian mass migration was kicked off by farming and drought problems. So what is evidence for global climate change? We look at ice cores, and they show the concentrations of CO2 and other greenhouse gases over many thousands of years. And what we can see is a clear increase in those gases, which makes sense because if you just look at simple combustion, the products of combustion are CO2 and water, and we burn a tremendous amount of fossil fuels that have been locked up under the planet for millions of years. We can also look at weather records. Over the past century or so, we've seen a gradual increase in average temperatures, and those increases are accelerating. Remote sensing by satellites, you can do a lot of very interesting stuff, measuring weather and water vapor and infrared radiation and other stuff with satellites. The other evidence is the evidence of your eyes, where every year it seems like there are more and more weather and climate-related disasters. Those aren't coincidental. There is an ice core, as you can see, it's quite cool. And so that ice core, if taken from the Antarctic or possibly the North Pole, I think they're usually taken from the Antarctic, will show 20 or 30 or 50 or 100,000 years of atmospheric conditions just by looking at the gases suspended in the ice or dissolved. So there you go. Okay, this checkout form may or may not be on the final version of this particular slideshow, but I think, yeah, I'll leave it up. So I would like you to fill in the checkout form, and you should also work some test yourself questions, and I have a handout that I will distribute as well. So that does it for the lecture in record time. And I'm going to add some nice backing music to it as well. So hopefully you enjoyed this format, and you should have taken some notes, guys. So, all right. Please direct your questions to Google Classroom or email me directly. Okay, talk to you soon. We'll work some problems, and you'll see, I'll give you solutions as well. Okay, have a good day. Goodbye.